Hey, my name's Dan Olds. I'm one of the beamline scientists at NSLS-II, and I'm going to be talking to you today about our work developing autonomous, real-time, AI-driven science for multimodal studies at NSLS-II. NSLS-II is a synchrotron, and what makes it unique is because of our extremely bright, very, very broad energy spectrum, we're really well suited to perform what are called multimodal measurements. Multimodal measurements are where you perform studies on the same material using different techniques. The two techniques that I'm going to be using and talking about today are X-ray powder diffraction and X-ray absorption fine structure. Now those are really long names, so as I'm talking about them, I'm going to refer to X-ray powder diffraction just as diffraction, and I'm going to refer to X-ray absorption fine structure as XS. So what's the difference between these two techniques? Well, in diffraction, you get a certain set of information that tells you about the atomic scale structural information of a material. So you can see things that are very, very short range and very, very long range, but you don't get any what we would call chemistry-specific information about the materials. You can't tell what the individual atoms are just from the diffraction data. Compare that to XS, where you do get that very specific chemistry information, but you're only able to see the short-range details of the structure. No long-range information is present in that data. So by combining the two together, we can get a more complete picture of the material, and thus we're able to advance our science and understand these materials on a much deeper level. The class of materials I'm going to be talking about are on studies of things called combinatorial materials. These are an exciting new class of materials that include things such as high entropy oxides and high entropy alloys. In these materials, they're composed of many, many different elements all mixed together. 5, 6, 7 different things all cooked together to make these materials. And part of the unique aspect of it is these materials have structure and important key features at different length scales. As in, sometimes you have to look very, very long length scales using things like diffraction and microscopy to see certain features. And to see other information on the short scale, you have to look at things like XFs or PDF methods or other such things. No one measurement is going to give you everything you need to know about a material to really understand the origin of its properties. So the samples that we're going to be looking at are created, these high entropy alloys are often created using sputtering deposition. Here's an example of one of those machines. And what happens is we have a substrate, sort of like a glass wafer, and then we have different nozzles that are going to jet down and spray different materials onto the surface of this wafer, coming in from different angles and positions. That means you're going to end up with a compositional gradient across the wafer. You're going to have all different sort of combinations of the elements represented on this single sample. Here is an example of what one of those looks like, a glass wafer mounted on one of the beamlines. And that shiny surface on it is because there is a whole bunch of different compositions on there. However, the question that we might have is, well, what exactly is on there? Right now, we see it's a wafer, but we don't know what phases exist where. How did these different elements in the combinatorial material combine to produce something? That's why you're coming to NSLS-II. That's why we ultimately want to produce a map like this one here, where we could exactly know how these different elements combined and what products you end up with. All right, so what's the holdup? We certainly have methods to measure these and determine material structure and phase. So given the size of the beam we have on my beamline, the PDF beamline, the total possible number of measurements on such a wafer is about 18,000. That's because we have about a 400 by 400 micron beam. And measurements on PDF take on the order of 10 seconds, which means given 2 days, we could fully map out this wafer. All right, so that might be tractable, but what about XFs? I told you we wanted to measure this using multimodal methods. Well, the problem is, in order to perform a measurement on the BMM beamline, which is an XFs beamline, those measurements take about 10 minutes, which means it would take 4 months to fully measure a wafer. But that's not even the biggest problem. The biggest problem is we don't want to measure just one wafer. We want to be able to measure a whole bunch of these different wafers and end up with a wide variety of information spanning many, many samples as quickly as possible. So how are we going to do that? Well, here's where artificial intelligence is coming in. We want to use AI to autonomously and simultaneously drive both beamlines while continuously leveraging all the information that's available. To do this, we do need to address the multi-fidelity aspect of the data stream, which is to say the data coming out of the x-axis is very different from the data coming out of the diffraction. And the beamlines are controlled on different systems. We need to make sure that the scientists are able to monitor what's going on. It's not a completely hands-free automatic measurement. We need to be able to step in and assist or intervene if the AI starts struggling. We need to ensure that we can perform this work safely and securely. And we want to do this in a way that's extendable. We don't want to just do this once and walk away. We want to be able to expand and add other techniques as we develop this multimodal methodology. So here's how it actually looked when we did it. We have a sample loaded on the PDF beamline, and we have a sample loaded on the BMM beamline. And simultaneously, data is being taken on, these are two identical copies of the same sample. We can see some of the data there plotted below. We feed that data into various algorithms and methods to analyze them and construct maps. And then from all this information of the best guess that we have about what's happening inside the material, we pass that up to an AI agent that's deciding what is the highest priority location to measure next. Where on the wafer on both beamlines, asynchronously, should things be being measured in order to complete the picture. Of course, it doesn't actually look like this while it's happening, but it does look like this. And I will say that this was absolutely the coolest thing I've ever done in my scientific career. Just to watch the beamlines sort of running themselves and talking to each other and making decisions and sort of real-time discoveries. Just a really wonderful, really cool experience. So if we step back and say, how does this actually happen? We have to think, how do we explore the unknown? And Galileo had some pretty good principles, right? We want to establish a basis of understanding through some initial observations. We want to develop a model around those initial observations. Draw insight from the model to inform on what additional measurements or experiments we might need to do, and then refine our model. And just because now we've brought AI and robotics and automation into the picture doesn't mean that we really want to take any other approach to how we explore these systems. So here's an example of data from the diffraction side of the beamline, the PDF beamline. And as you're seeing, these are patterns measured. Every little squiggle here is telling us something about the atomic scale structure. And we've plotted what we call a waterfall plot. So this is sort of on the wafer as a function of position, where these 6 different patterns had been measured about 50 millimeters apart in total. So based on this, the agent might say, oh, you know, I think I'm going to measure up here next. I haven't seen this side of the wafer. And then I'm going to look at that and go, now I want to measure down here. Or, oh, this looks interesting. I see a big change. Let me grab this data point in there. So when we put all this together, at the end of the day, here's an example of the full data collected. What we want the AI to sort of be doing while this is going on is clustering the data, making decisions to automatically sort out what's there. If we take the full data set and we perform something, in this case we perform a relatively simple algorithm called k-means on it, we can say, oh yeah, this clusters it into regional, realistically regional clusters of the data. And we clearly see differences between phases across the wafer. Again, this is just a left to right view. It's not the full 2D. But I should emphasize, we didn't force the algorithm to do that. The fact that it's clustering everything together as it does is a pretty good indication that it's working. So I'm going to take this data, going back, looking at the full picture, and I'm going to sort of change to a heat map view. So this is now just a heat map of those diffraction patterns, but the same thing that we saw. And now to confuse you just a little bit, I'm going to rotate the data about 90 degrees. We end up like this. And I'm going to show you in real time how the AI explored this. So you can see each of these bumps is where it's choosing to do a measurement. You can see it initially just sort of coarsely maps everything out, and then it's finding little areas that it wants to investigate more in detail. It's sort of mini campaigns to say, ooh, what's this over here? Or, oh, I still want to know more about that region. So as it runs through and it's doing this, the whole idea is this is autonomously driving the beamline. It's doing the exploration in real time for us. So looking forward, here we are. We've actually invented a new way of doing these multimodal studies at NSLS-II. I want to emphasize this was made possible by our Blue Sky framework, which is the software we use to run the beamlines. And beyond this initial work that we've done, we've opened the door to new and novel ways of utilizing the beamlines and other techniques. Because this was really one of the world's first truly multimodal light source measurement that used AI to perform real-time analysis and control of multiple beamlines at the same time. And again, just one of the coolest things I've ever done. I need to thank all my collaborators who really helped make this work possible. And I want to say thank you very much for listening, and I'm happy to take any of your questions, comments, or whatnot by shooting me an email. Thanks a lot.